Hello everyone and welcome to the channel. Now this video is going to be the next part of your chemical thermodynamics, and it's going to be a very important topic which is from from the subject, and we'll be talking about Clausius Clapeyron equation, right? So this is one of the most important equations when we talk about the phase transition. So from the phase transition, I mean when a particular thing changes from, let's say, from solid to liquid, or it changes from liquid to gas, or it changes from gas to solid, or whatever the phase transition happens. That means from one phase to another, if the particular thing is being like the transition is happening. In that particular case, to solve all the things, we use Clausius Clapeyron equation over there. Now there are two forms of this. One is called as the only the Clausius equation, and the other one is called as Clausius Clapeyron equation. So we'll talk about both of them in detail today in this particular video. We'll also solve some questions which have been asked directly from this in the CSIR net exam. Talking about this phase transition part, that means the phase diagram and the one component, two component system. So that is totally a different topic that I'll cover in some separate video. But here we will be just stick together for Clausius Clapeyron equation. Alright. So I'll try to cover this up in the next few minutes, and stay tuned for that and watch the video carefully and completely. And before starting anything, I would like to request you that if you are new to this channel, do subscribe to this channel. We are also available on Instagram, Facebook, and also we have a Telegram group. So if you want to get into the discussion, if you want to discuss questions among the other net aspirants, and if you want, you can join Telegram group as well. You can join us on the Instagram, you can follow us on Facebook. All the links are there in the description, so do check them out as well. So let's start this particular topic. So we'll start from a particular Maxwell relation. The relation goes like del P by del T at constant V is actually equals to del S by del V at constant T, where you know the terms like P is pressure, T is temperature, S is entropy, and V is volume. So this is the one of the Maxwell relation which you already know. Now if I multiply and divide by the temperature on the right hand side, so I'm going to get del P by del T at constant V, and that is going to be equal to T, and it's going to be del S by T del V at constant T. Alright. Now we know that from the second law of thermodynamics, we have this that like from the formation of the entropy, we have this that dq is actually equal to TdS, right? So we can just substitute its value over here. So what we are going to get is dp upon dt is equals to dq upon t and delta V, or you can write it like V2 minus V1. Okay, so the change in volume. So this is going to be called as your Clausius equation. Okay, this is called as your Clausius equation. Clausius equation. Now this is limited to be used when you have a particular transition happening in between of any of the phases. So any two phases, if a certain thing is changing between any of the different phases, whether it is solid, liquid, liquid gas, or any of them, so you can use this Clausius equation. The other part, which is called as Clausius Clapeyron equation, is applicable only for a particular phase transition, that is from liquid to vapor or from liquid to gas. Okay, so if a particular transition is taking place between liquid phase and a gaseous phase, in that case we call it as Clausius Clapeyron equation. Now here what is going to be different is, the only difference is that over here in this particular formula, in the place of this dq, will replace this by dH. Okay, that is the enthalpy. So the equation will be like dp by dt, this will be equal to delta H, and since the change in like the enthalpy over here will be the enthalpy of vaporization, so I can write down delta H vaporization divided by, and T, it will be volume, and this is going to be Vg minus Vl. Okay, so volume of gas minus volume of liquid. So this particular equation is called as Clausius Clapeyron equation. Okay, this is called as Clausius Clapeyron equation. Now remember one thing, that the Clausius equation has been just derived for a particular phase transition, that is for liquid to gas phase transition, and that's what we call it as Clausius Clapeyron equation. Now in this particular equation we can also integrate it further, and we can have an integrated form of it. So let's try to find out that also, and we'll do some part of it and then we'll go for the questions. Now this was our Clausius Clapeyron equation, and since we know that the transition is happening between liquid and gas, as I told you, Now obviously the volume of gaseous part will be very much greater than the volume of the liquid part, right? Because gas occupies a larger volume than the liquid form, obviously. So we can just substitute Vg in the place of Vg minus Vl. We can put that over there, and rest of the things will keep it as it is. So we'll have dp by dt, that will be equal to delta H of vaporization divided by tvg. Okay, now I can just have an integrated part of it. So what I can do is, since this equation, whatever equation we are doing, is for ideal gas, so what I'm going to do is I'm going to use ideal gas equation in order to substitute the terms over here. So from the ideal gas equation, what I have is PV is equals to RT for 1 mole of gas. Okay, for 1 mole of gas, for 1 mole of ideal gas. So in that particular case, I can write down V is equals to RT upon P. So I have considered that the gaseous part of it is actually ideal gas. So I can just substitute it over here. So what I will get is dP upon dt is equals to delta H of vaporization divided by T, and in the place of Vg, that is velocity, volume of gas, I can put RT by P. So it will become RT by P. So basically the equation overall, it will become dP by dt is equals to delta H of vaporization multiplied by P divided by RT square. Now I can just I can just resubstitute the variables, or redistribute the variables basically. So I'll have dP by P, and that is equals to delta H of vaporization divided by R, and it will be dt by T square. So what I can do now is I just have to integrate both sides. Okay, so if I integrate, these things are going to be constant, so let it be. I'm just integrating it over here, so I'll be writing out whatever I'm going to get over here in the on the screen. So on this side I'll have ln P. Okay, so that's what I'll get, integration of 1 by P, and the integration of 1 by T square will be equal to, so this is going to be delta H of vaporization divided by R, and this is going to be equal to 1 by T, okay, minus 1 by T basically, and here you will have from T1 to T2. Okay, so if you substitute the values, so basically your equation, your Clausius Clapeyron equation, the integrated part of this Clausius Clapeyron equation will come out to be yeah, so this will be ln P, and here it will be from P1 to P2, or you can write down that ln P2 upon P1, this is actually going to be equal to delta H of vaporization divided by R, and in the bracket I'll take minus sign outside, this minus sign, and it will be 1 by T2 minus 1 upon T1. So this is one of the form of your Clausius Clapeyron equation. Okay, so I'll just put it in a box. So we have more of the form of it. We can just remove this negative sign, and by that this bracket will also change. So I can also write down ln P2 by P1 will be equal to delta H of vaporization divided by R. In the bracket I will have 1 by T1 minus 1 by T2. So I can write down like this as well. So you can write down the equation in any of the form, but remember that you should memorize, or you should be able to identify the correct form of the equation. Okay, so we have more form of it. Let's try to understand them as well. So ln P2 by P1, which is actually equal to delta H of vaporization divided by R, and it was 1 upon T1 minus 1 upon T2. This is one of the equation which I personally use when I solve questions. Okay, so you can use in the same way, or you can convert this ln into log base 10, so it will become log base 10, and it will be P2 by P1, and on the other side you will have delta H of vaporization, because when you convert ln into log base 10, basically you have to multiply by 2.303. So either I can write down 2.303 here, or I can take it to the denominator on this side. So it will be 2.303 R, and in the bracket I will have 1 by T1 minus 1 by T2. So this is going to be another form of my integrated form of my Clausius Clapeyron equation. Okay, now you can have this equation in many forms. You can either write down this particular equation in the form of straight line. So if you are plotting a curve on the straight line where you are taking log P2 by P1 on the x-axis, and you are taking 1 by T1 minus 1 by T2 on the y-axis. So basically what you are going to get is a straight line having slope delta H vaporization upon 2.303 R. So this is going to be the slope of that equation, or slope of that line. Okay. There are some other form of it as well. So you can have this as well, that P2 by P1 is equals to e to the power delta H of vaporization upon R, and in the bracket it will be 1 by T1 minus 1 by T2. So this is also one of the form, or you can write down that P2 is equals to P1 e to the power delta H of vaporization divided by R, and in the bracket it's 1 by T1 minus 1 by T2. So remember, all these things are in the power of exponential. So this is also one of the form of it, that is called as the exponential form. This came from this equation where I have just removed this ln and taken all this term to the e to the power. Okay, so these were some of the forms of your Clausius Clapeyron equation. Now let's try to understand the application part of it. So how we can use this equation to identify the effect of pressure on the melting point. So let's try to use that. Now let's discuss the effect of pressure on the melting point of a certain system. So for melting point, we have to take a particular phase transition in which basically your solid and liquid are in equilibrium with each other. Okay, so your solid phase has to be in equilibrium with the liquid phase over here. So since we already know that dP by dt is actually equal to delta H of vaporization, we were keeping that up till yet. But since solid is getting converted into liquid, so we can use the equation in the same form. Here we'll write down delta H of fusion, okay, or delta H of melting, and divided by, we'll write down temperature of fusion or temperature of melting. We'll just write down temperature of fusion, and it will be volume of your liquid minus volume of solid. Okay, so that's how it is going to happen. Now we know that, but for any system, your volume of your liquid part will be greater than the volume of solid part. Okay, so volume of liquid part will be greater than the volume of solid part. So we can just have that particular thing, that this particular value, that is VL minus VS, will be positive. All right, so yeah, that is going to be a positive term. So this particular part became a positive number. So once we got this, that this is going to be a positive number, so that means what, that overall this value delta H of fusion will also be a positive, temperature is going to be positive. So basically dP by dt for this term is going to be a positive term. So what we can say, that melting point of such substances are like that is going to rise with the increase in pressure. Okay, so this is going to be applicable for all those system in which volume of liquid phase is actually greater than the volume of solid phase. Okay, so what I can say is that the melting point, okay, melting point of such systems, melting point of such system rises with increase in the pressure, with increase in pressure. That's what I can say right now. Now we have certain more types of systems in which the thing is reverse actually. Now we have certain other type of system as well, like your ice is there, then you have bismuth, okay, then also your gallium is also there. So under these systems, what happens, that volume of solid part is actually greater than the volume of liquid part. You might know this thing from the solid liquid curve in the phase transition. If you don't know, you might have seen this in the practical aspect also, that if you fill a particular water bottle completely and put it in your refrigerator, you will find out that after some time, when the ice will be filled out, when the water will freeze and it will get converted into ice, your water bottle will expand a little bit, right? So that means what, that volume of solid phase is actually greater than the volume of liquid phase, and that happens because of the hydrogen bonding which is caused over there. So that means what, that if I talk about this particular term, so your VL minus VS is going to be negative, and if this part becomes negative, obviously your right hand side of the equation becomes negative. So what I can say, that dP by dt is going to be a negative term. So what I can say right now is that melting point of such system, okay, so melting point of such system decreases, okay, with increase in pressure. So decreases with increase in pressure. So that's what it means. It means that for such system in which your volume of liquid phase is greater than volume of solid phase, like your sulfur is there, your wax is there. There are a lot of systems where your volume of liquid phase is greater than volume of solid phase. So over there, your melting point will rise with increase in pressure, whereas the system where your liquid volume is smaller than the volume of solid phase, there your when you increase the pressure, your melting point is going to decrease. So this is one of the direct application of your Clausius Clapeyron equation in finding out that how your melting point changes by changing the pressure. So that's all about the explanation part of this particular equation. Now let's take some questions which have been asked in previous years of CSIR net exam, and we'll try to solve them up. Alright, so let's discuss this question which was asked in CSIR December 2016 exam, and the question says that the volume change in the phase transition is 0. Okay, from this we may infer that the phase boundary is represented by. So basically this is actually from the phase transition, but yeah, you have to use the same Clausius Clapeyron equation to solve this question. Now since we know that from the Clausius Clapeyron equation which we did, from the Clausius equation basically we know that dP upon dt was actually equal to delta H upon T delta V, right? That's what we were having, like V2 minus V1 or T delta V. That's how we can write down this equation. Now here you can say that in the question it is given that the change in volume or the volume change is actually equals to 0. So if this part is equals to 0, so what is going to be the equation? Okay, so dP by dt will be equal to your delta H upon 0, because whole this thing, like in the denominator it will become 0, and anything divided by 0 is nothing but infinity term or not defined term, so which is not defined in mathematics. So you can say dP by dt is equals to infinite, or you can also say that not defined. Okay, not defined term. Now this dP by dt is nothing but it's going to be about the slope of the equation. Whenever you have some curve from y and x, so the slope is actually given by dy by dx. So in the same way, if I have p and t over here, so the slope will be dP by dt. So dP by dt is nothing but we are talking about the slope over here, and the slope can also be represented as tan theta. Okay, so tan theta, that means theta will be the angle made, like if this is the slope, so this theta will be the angle basically. So tan theta is going to tell us this. So if tan theta is equals to dP by dt and dP by dt is equals to infinity, so we can say that tan theta is equals to infinity. Now if you know the values of tan theta, there is a table for calculating the values of tan theta. So tan theta is actually infinite at 90 degree. So that means what? That tan theta is equals to infinite when I have tan 90 degrees. So that means my theta should be equal to 90 degrees. That means the angle has to be a 90 degree angle. So if this angle is 90 degree, that means what? That this angle has to be like this, right? This is to be the 90 degree angle. So obviously the line which shows 90 degree angle is nothing but your option number 1. So you can see over here that the line shows 90 degree angle. So like that you can say that option number 1 is the correct option. So this is how we have to utilize our knowledge of Clausius Clapeyron equation. Now it's not necessary that from the exact equation they will ask question. They can ask you from any point of the derivation of that Clausius Clapeyron equation. So from there you can infer and you can write down, or you can just derive the equation and calculate it. So I hope this is much clear to you guys, right? Let's take one more question which was asked in GATE exam, and just we'll wind up the video then. Alright, so this question was asked in GATE 2018 exam, and the question says that the enthalpy of vaporization at its boiling point, the boiling point is given to us as 200 Kelvin, and the enthalpy of vaporization is given to us as 15.3 kilojoules per mole. Now it says that if the molar volume of the liquid and the vapor at 200 Kelvin, that is at the boiling point, is 110 and 12,000 centimeter cube per mole respectively, then the slope dP by dt of the liquid vapor curve is, or liquid vapor boundary is. Now it's the same thing which we have done just now. So we have to utilize the same formula, we have to apply the same formula to calculate it. The formula is like dP by dt will be equal to delta H of vaporization divided by yeah, so it will be divided by T and delta V, or V2 minus V1, because that's how we will write down, or Vg minus VL. Basically, to be more precise, I'll write down in this form, Vg minus VL. If you remember, we have done the same, we have substituted the same values of the previous derivation. So you just have to put the values which are given to us. Now delta H is given to me as 15.3 kilojoule per mole. I can write down it as 15.3 into 10 to the power 3 joules per mole. Why joules per mole? Because at the end I have to convert, like I should be getting my answer in joules per meter cube, in order to convert that into Pascal and then convert it into kilopascal. So I have just converted into joules per mole. Okay. Volume is given to us as Vg is given to us as 12,000 centimeter cube per mole. Okay, and VL is given to me as 110 centimeter cube per mole. So I have to convert that into meter cube just in case to get joules per meter cube. Okay, so I have to convert this into meter cube. So it will be 12,000 multiplied by 10 to the power minus 6, and then it will become meter cube per mole. Similarly here also I have to convert that, so 110 into 10 to the power minus 6 meter cube per mole. Now I just have to substitute all the things over here, and temperature is already given to me as 200 Kelvin, so I don't have to convert that. So this is all unit conversion work which I have to do, and next I have to just substitute to get the answer. dP by dt is what I have to calculate. Delta H will be 15.3. So 15.3 into 10 to the power 3. Okay, that's what I will get in the numerator, divided by, I'll have 200 in the place of temperature. Volume of gas, I'll write down 12,000 minus 110 and into 10 to the power minus 6. So I have just taken these two things common from both the sides, so I have just taken it outside. So when I will solve this all, what I'm going to get is I will be getting dP by dt is equals to 15300, and divided by, in the denominator when I will multiply all the things, I can use my calculator because it's a GATE exam. So I'll be getting 2.378. After dividing this, my dP by dt will come around 6433.97. This is going to come in joules per meter cube. So that is going to be my in joules per meter cube. So 1 joule per meter cube is equals to 1 Pascal. So I can write down it in 6433.97 pascals per Kelvin. Okay, so per Kelvin. Now since the question they have asked in kilopascal per Kelvin, so I have to convert this into kilopascals. So I just have to divide it by 1000. So I will get 6.43. I just have to write down up to 2 decimal places. So 6.43 kilopascal per Kelvin is going to be the answer of this. Okay, so the answer is going to be 6.43. That's going to be the correct answer. So that is how we have to use Clausius Clapeyron equation to solve. There are many questions which are asked from this particular topic. Every year you will find out one or the other question from Clausius Clapeyron equation. So I will recommend you to solve previous year's question based upon this particular topic. I hope whatever I taught in this video was helpful to you. You guys understood it well. If you have any doubt, you can ask that in the comment sections below. And that's it for this particular video, guys. Practice question, that is very important, and if you'll keep on practicing, then these videos are going to help you to like get through all your physical chemistry fear, and you'll be able to be a master in physical chemistry. Okay, so don't worry about that. I'm here to teach you all the topics from basically from the physical chemistry, and I'll try to improve your physical part. So that's it for this particular video, guys. I'll try to bring up another topic in the upcoming video. So thank you so much for watching, and if you're new to this channel, please subscribe to the channel. If you like this video, give it a like, and if you want to ask anything, you can ask that in the comment sections below. Thank you so much and have a great day. Stay safe and take care of yourself.